Let's learn a bit about earthquakes and let's take some notes so we have some understanding of what's going on in general with earthquakes and with what happened in Appar. Notice these images, or you can see there's a lot of damage. I enjoy pointing out certain things with these earthquakes. One thing is, look at this guy here, trapped between the two layers. Okay, so earthquakes are doing pushing and pulling forces. You can see the result is a lot of damage. You can see here, this is in Japan. This whole upper freeway fell over. This is in Asia. A big pothole formed and kind of took part of that truck inside the ground. So what is an earthquake? So here's our definition. It is the movement of ground caused by this release of energy, right here, this energy when rocks along a fault are moving. So think about the changes in matter that we see here. And we know that when there's changes in matter, it's caused by energy being transferred somewhere. And when energy is being transferred, it's affected by forces pushing and pulling. So our triangle that we're always talking about definitely applies here. Okay, stress. Not the kind of stress we feel, but stress. The Earth crust moves, and we know it moves because of moving between the plate boundaries, plate tectonics, that's evidence. The crust is either squeezed, stretched, or twisted, and the amount of squeezing and stretching is called stress. So if we pulled apart a rubber band, that's the tensional stress. It's moving apart away from each other. And then compressional or squeezing stress is when things are being pushed like you did on the simulation and you push the molecules closer together. And then sometimes the stress just grinds right past it. So it's like this scraping motion. And that's the shear stress that we see down here. But all stress is this motion, this deformation that we've talked about. Okay, so that compressional stress happens at a plate boundary where the plates are coming together. And when the plates come together, we call that a convergent boundary. So there's places in the planet where there's an ocean crust diving under a land crust, and that causes a trench or a subduction zone to happen right here, subduction. And you get that deep, dark ocean trench that goes super deep down, like in Nemo. Convergent boundaries also can cause volcanoes to form here. So this could like make some lava come out, and this could be a volcano with like some ash. And it can also make very tall mountains form. So when this pushes down and squeezes up, these mountains here can grow taller and taller. All right, tension or pulling is when you can see this stretching and pulling apart, and that's called a divergent boundary, like it's dividing or divorcing, going away from each other. We usually see that in the ocean ridges, plates that are separating in the ocean, like the mid-ocean ridge, and we can sometimes see it on land where the land is pulling apart. Like there's places in East Africa that are splitting apart and opening up, and in Iceland also. When we have the crust pushing in opposite directions, one's going north, one's going south, for example, that's called shear stress or a transform boundary. And the really famous one is the one that we live on, which is the San Andreas Fault. That one doesn't cause mountains or valleys or lava to come out. It's just the ground moving past each other, scraping past. So you can see here, tensional stress causes these cracks like in Afar. Compressional stress makes volcanoes, also like in Afar or other places in mountains, and then the shear stress just scrapes tectonics past each other without making high places or low places. Okay, so when we look at this at a rock, when we're putting these stresses or forces on a rock, we have the pushing, we have the pulling, and then this one just pushes in opposite directions. So it's a push or a pull, however you want to look at it, in opposite directions. But these are all forces. Okay, so when there's too much stress on the rock, then it deforms like we were looking at in class. It'll change its shape. We saw that in the simulation. We saw that with the foam that was bending in class and then going back down. And too much of that stress or too much deformation places a strain, and then it will break, bend, and tilt the crust and reshape it. And then the breaking, when it actually breaks, that's what becomes the earthquake, because the energy is sent out in waves that we can feel. So you can see this right here is a transform boundary. This plate is moving this way. This plate is moving that way. And you can see right here how much it's moved. It was, one continuous dry lake bed, but now it's moved this direction off of it. This is also rock that was switched. You can see these swirls, and it's been strained and it's broken and reformed. Okay, so what happens with the earthquake? So the fault is locked. Stuff usually isn't moving. It's like it grips like the foam pads. They have rough edges and they lock into each other, but it's still trying to move. And so friction, there's a little force of friction, that resistance to movement prevents it from moving. So we call that locked, a locked fault. But that stress is still building up. One plate's still trying to move this way. The other plate is still trying to move this way. And so this stress is building up in the form of potential energy. So even though it's not moving, it's push, 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 push. And then when it actually does move, all that energy releases and it becomes kinetic energy. So the friction's overcome, the rocks move, they release all their energy. It's now kinetic energy, and there's this vibration of that movement of the crust, and it goes in what we feel is like these seismic waves. And that's all energy. Okay. So a fault is where stress builds up that causes the crust to become strained, and they are always areas of high earthquake activity, meaning most earthquakes happen along a fault or plate boundaries. Okay, so the North American plate is east of us. It's California and pretty much the rest of North America. And then there's this little Pacific plate. It's not little, but the Pacific plate is part of the Pacific Ocean, and our little piece right here where we are. And we're moving kind of northwest, and this plate is moving southeast, and that's the San Andreas Fault. So that's where we are, just kind of scraping along, and maybe someday we'll be next to San Francisco. Okay, some other terms we've probably heard just because we live in California: the epicenter of an earthquake and the focus of an earthquake. The focus is where the earthquake first starts inside the earth. So it's way down, if you look at this cross section, way down inside the earth where the slippage happens. Sometimes we just think of the plates as being these things on top, but remember they're thick, miles and miles thick, and a lot of times that scraping and fault moving happens miles and miles deep down inside the earth. So wherever that slip happens is called the focus. And so the way I remember it is the focus is where it first happens, and they both sound like focus first. That's how I remember it. The epicenter is a location for humans, like on the top of the surface where it happens. So if we were like just gonna say, oh, this earthquake occurred 10 miles south by southwest. Like we would know what that meant. So what we do is we take the focus, we come up to the surface of the earth and we can go, oh, that happened in Anaheim, California. So it helps us put it on the map, like what is it near? Even though it's way down inside, we can come up and be like, oh, I know where that city is, or I know where that place is. So it's for us to understand where it happened. So that's the epicenter. And that's usually what's reported because we don't know what all those coordinates mean inside the earth. Only scientists do. Maybe Google Maps does. I don't know. Okay. Now, earthquakes come in waves. They travel in different waves, and the waves, just like any other wave, has energy. So earthquake waves are just like light waves, just like ocean waves. All waves carry energy. And the way that these waves carry energy are in kind of phases. So the first wave, the primary wave, comes first. And then the secondary wave, just like it sounds like, comes second. And then the third kind are these surface waves. So we're going to talk about each of them. And you can see right here, here's the primary wave coming to the detection station. Here's the secondary wave. And then here's these surface waves. And I hope you can see, let me find a different color. Primary waves are this destructive, secondary waves are this destructive, and the surface waves are a lot more intense than the primary and the secondary waves. Okay, so just some wave review that you should know, and if you don't, here you go. A wave's top part here is called the crest. If you can't read that well, I'll write it worse for you. This is crest. From top to top or bottom to bottom, that's the wavelength. If you're just measuring the same location of the wave as it travels, that's the wavelength. The height of the wave is going from this middle line to the top, or the middle part to the bottom, and that's the amplitude of the wave. So it's not the whole very top part to the very bottom part. It's from the middle to the extreme, either bottom part or the extreme top part. That's amplitude. And then the trough is the low part, like what the animals drink out of is a trough that holds stuff. So that's what the trough is called. Okay, those are the basic parts of a wave we need to worry about for earthquakes and other stuff we're going to learn about later. Okay, so this primary wave, it's P wave because we just give it a nickname, primary wave, P wave. It does a push and pull movement, so that's convenient. So not only does primary mean the first, but it also pushes and pulls, so all that P alliteration from English is helpful. So it squeezes, it pushes, and it yanks it back out, that pulls, and it moves really fast. So of the three seismic waves, this is the faster moving wave, and it has the ability to move through both solid things and liquid things in the Earth's crust, which is something to remember. And so it moves like this. So this wave is squeezy, and it just moves through while it's squeezing together. This shadow zone is interesting because it helped us figure out why P waves move through solids and liquids and why S waves do not. So if you remember, the inner part of our planet, the inner core, is solid. That is not a good color for us to see that. It is solid. The outer core is liquid. The mantle is kind of a squishy solid, but it's solid. And the crust is also a solid. Okay, so if we know that, it's kind of layered. Solid, liquid, solid-ish, and then solid again. So these P waves, when an earthquake happens, so let's look at this graphic. Here's our epicenter, where the earthquake's coming from. The P waves are moving through all of the layers. So you can see all these P waves. But there's this weird layer, and my recording head is in the way, but there's a place where they're not detected. And sometimes when the waves are moving, like I was trying to explain, When they move, they change their speed and direction when they enter a new medium. So if they're going like from sand to rock, those are different mediums. If they're going from rock to like agricultural soil, through an ocean crust, through water, those are all different kinds of mediums. Different particles of matter make up different layers of our planet. And so every time we have that happen, we change the speed and the direction that the earthquake wave is moving in. If it's moving from a solid crust to a semi-solid mantle, if it's going from the outer core, which is liquid, it'll change the speed, velocity, and the direction of these earthquake waves. And so you can see they'll bounce. Each of these dark lines here represents like a change in layer, and you can see they're going through, and then they hit something else, and then they bounce off, and they change their direction where they're going. And for some reason, this shadow zone happens where there's no earthquake waves detected in these areas. And because of the way we can track the movement of the speed and direction changes with each layer, we can find these shadow zones. And so that's an important tool that scientists have used to be able to detect what's going on in our planet and to understand that P waves move through everything, but S waves don't. And if I had an S wave shadow zone to show you, it would actually be like larger. The S wave is like this big shadow zone because it can't go through this liquid outer core. So S waves will bounce off and kind of go like this. This is messy, but that's what kind of happens with the blue. And so this whole area down here would be this S wave shadow zone. No earthquake, no S waves from the earthquake would be detected down here. Only P ones. Oh, wait, what happened? That was weird. Okay, secondary waves. All right, the secondary wave is S, and it moves perpendicular to the wave direction. So that's kind of hard to think about. If the wave is moving this way, the S wave moves perpendicular, so up and down. So it's the one that looks like a snake. It's going up and down, and it moves kind of a medium speed. It's the second fastest of the three, but it can only move through solid things. So when it hits a liquid, it actually changes speed and direction. It will change the speed and direction when it hits a part where there's liquid, a lake, underground aquifer, anything that has liquid in it, that layers of the earth, there's a liquid layer. So when that happens, it kind of bounces off and goes a different way because it can't go through the solid part. Okay, and then the third one are these surface waves. These surface waves only go on the surface of the earth. So before, if this is the flat place and here's our cities and all of our stuff, P waves, remember, will start at the focus and they'll radiate out in all directions. An S wave will also come from the focus, but the surface waves don't start until these waves get up here on the surface of our crust, and then they'll radiate out like that. And they can move in all kinds of directions. So there's two kinds named after the guys who discovered them. So some guy's last name was Love, so it's the Love waves, and the other guy was Raleigh, so the Raleigh waves. And they can move all kinds of directions. They can go side to side. They can go up and down. They go back and forth. They push, they pull, and they move really slowly. So if they're doing all these crazy movements slowly, they're going to do the most damage. So if a P wave moves really fast, but it goes back and forth, but it goes really quickly, okay, we feel it. And then an S wave moves up and down, but it moves pretty fast also, we feel it. But if that surface wave, let's find another color for surface wave. If the surface wave is going back and forth, it's not a good color, that's the same color. There we go. If it's going back and forth, up and down, back and forth, up and down, but super slowly, just think if that's your house sitting on top of all that, it's gonna like wreck your house. So it causes the most damage because it moves so slowly and because it moves in all the directions. It's kind of like a wild, crazy ride.